Right. So let's get started. Last to last class, right? Last to last class, we were trying to figure out a method for finding the minimum spanning tree, right? Method for finding a minimum spanning tree. Yeah. So obviously, what do we start with? We start with a connected graph. Sorry, once again. Yeah, we start with a connected graph. So any connected graph will do. But the edges now have weights. Okay. So the graph that we begin with must be connected. If it's connected, has a spanning tree. Okay. But that we know already. We also know how to find it out algorithmically. But now we are interested in more, right? We are interested in finding a spanning tree which has the minimum weight. Now there can be multiple spanning trees which have the same weight, same minimum weight. Okay, but we're interested in finding one of them. So they could have weights. So I'm just putting some simple weights. 2, 3, 3, 5, 5, 7, 7. Okay. Let's also maybe label them V1, V2, V3, V4, V5, V6, and V7. So before I move forward, would anyone like to summarize what have we already done under this particular topic? Yeah. What has been, it's not like we are doing this particular thing for the first time. What has already been done? And then what do you think is left to do? What have we already seen in this? Okay. So we have already seen a method, right? We already have a method that was described the last time, and we had also proved it. And that was, I'm just writing it in line, sorry, because as an algorithm, it's not so nice, okay? But mathematically, it works, okay? So method is, can anybody say what was the method we had used to, I'm not asking for a proof, but just the method to extract the minimum, to extract a tree from here, obviously using the edges that we already have, which has the smallest possible weight. Yes, exactly. That's right. So yeah, it's okay to say removing. No, it's not okay. So it is. So so you have said two things, and I think it's good for all of us to see that they are not the same. They are not equipped. They're not the same thing. So if you say that start by removing, I mean, you would obviously also understand that this is not correct. Removing just max weight edge. Yeah, this is not correct. This is not precisely correct, right? Because the max weight edge might not be good to remove, right? You can already understand, right? If it's an essential edge, yeah, it may not be. So for example, something like this. Even if this is 100, you have to take it. Yeah. So obviously it's not that, but obviously I understand what you're trying to say. It was that you look for cycles and then from the cycles, you remove them. Yeah. So just I'll say from cycles, remove max weight edges. And obviously you can't do this at once. You have to find a cycle, remove the max weight edge. Now in the resulting graph, you have to look for a cycle and then remove and so on. And eventually you will be done. And we had proved it. Okay. We got into a little bit of a mess, but I think but we ended up proving it. Okay. So this is fine. But so can anybody describe or can anybody mention why algorithmically, okay, the word algorithm might be framed in many ways in different kinds of exams. It depends, but I'll just put it in this language because we have been using it. Algorithmically, why is this not a good method? Okay. So mathematically, it's correct. We have proved it, but algorithmically, not good. That's right. Yeah. How do we figure out? So if graph is given, how do you find out all the cycles and so on, right? That's a little difficult to do. I mean, yeah, at least we don't know. Okay, a fast way. So yeah, that is the problem because looking for cycles seems to be because at each stage we have to find a cycle, and then it's how do we do that? So yeah, in that way, this is at least it seems to us that it's not good. It's not a good method, but I don't know. One can make it work maybe. Okay, so that's what we have already done. Okay, so today we would like to not just have a method, but also have a method that is made up of very simple steps. Okay, maybe a large number of steps, but simple steps. Okay, each step should be very simple. Okay, and that is what an algorithm is. Okay, that is what an algorithm is. A lot of questions in, if you're looking at from the Olympiad perspective, involve algorithms. So they will not specifically ask for an algorithm, but if you describe a method, yeah, the first player does this, second player does this, and then this is basically a prescribed algorithm. And so basically a process. So this is just one of those kind of questions. Also, it also theoretically is a very important question because we have already seen spanning trees were crucial in a lot of simple problems, and we'll have more problems coming where it will be useful. Now you're looking for an algorithm. So anybody has thought about this, or yeah, how what would be a more simple to describe way to do this? Yeah. Yes. Yes. that is I think that is a good method. Yeah. So let's write that. And so before I write that, I will put a phrase to it. That is, you're building it from bottom up. Okay. Maybe this is not the right usage of the phrase, but I guess we can share the language. Yeah, bottom up. So this kind of phrases can help you think clearly also. That's obviously not necessary. Okay. So he's trying to build the graph from, from the empty. So you can look at, so maybe it's good to simultaneously keep this, and otherwise I'll have to remove and so on. Right. And now we can one by one decide which edges to put in. Okay. Yeah. So naturally, it's again a very natural algorithm. It's a greedy algorithm in the spirit, in the same spirit, because we are just trying to do the best at each step. And what is that? So at ith step, okay, select an edge with minimum weight that does not form a cycle with the already selected edges. Yeah, that's all. Yeah, at each step we're just thinking about doing the best thing at that stage, at that step. Okay. So is the algorithm making sense to everyone? Is the method making sense? Yeah. Let us just execute it here, though, even though it's very simple, but let's just do it. This can also help us to think of a proof. Yeah. So obviously the first step will be to pick the smallest edge then, right? Because smallest, the first step, the first edge that you pick, it does not matter. It will not form a cycle, obviously. So we pick, so this is a step 1. Let's also keep the numbers here. What are we going to pick in step 2? Yeah, one of the two. So either V1, V7 or V2, V7. And sorry, we can pick any one of them. So yeah, let's just pick this one because no cycle is formed and that's clear. Okay. Yeah, once again, in the third step, there is no problem. I think the way I've given the graph, there will never be a problem. So it's not a good graph. Maybe, no, maybe we will have, let's just do it patiently. So we have, maybe we select this one in the third step. The key is to be able to prove why this will give us the minimum. Okay. 3 and yeah, there will not be any problem the way I have given the graph. Maybe this is again, we will be in this one, 3, then we'll pick a 5. Yeah. And then we can pick a 7, or no, we'll pick a 5 again, right? So again a 5. And then, then maybe, okay, so I'm sorry. I'm executing it correctly, but my explanation is wrong. Okay. Yeah. So can anybody just say what should be the third step? I mean, the third smallest edge, objectively smallest edge is V2, V7. Yeah. But we are not picking it because it's going to form a cycle. Okay, I didn't say this. It's a trivial thing, but I said it. Yeah. Okay. So we are not picking it because it will form a cycle. Okay. And then we are moving on. The rest of the things are making sense. Right. Yeah. Anyways, okay. So that was just a minor thing. And in this way, you can understand, right? It just goes on, makes a 7, and then it stops. And this is the thing. And it's quite easy to believe in this case that this is a minimum. Okay. Because yeah, you can't pick both the 2s and you have to leave the 1. And if you leave the 1, but you have to still, if you want to even do it for this case, to maybe do a few caseworks and then explain. But we want to prove it in a more elegant way so that we can, in general, give a proof. Yeah, why not? Because weight is 3. Oh, but it forms a cycle. Sorry, yeah, it formed a cycle, so we should have not taken it. Right. Perfect. Yeah, we don't need to take it. We should not take it. Yes. So that is, but it was clearly wrong. I don't know what. Yeah. So again, yeah, that's another example, right? That it would come in as a candidate, but you would not take it. Okay. So algorithmically speaking, what the first thing that one has to do, okay, fundamentally, the very first step, okay, the step number 1 that maybe it has to do is, because if you get the graph like this, right, then the computer has to first sort the edges. Yeah. Some of you may have done a few sorting algorithms if you have done Python or C a little bit. Okay. But I will not go into the details of that. It's not graph theory for now. So sorting the edges in increasing order. Yeah. Oh, because it was forming a cycle, right? But there is no edge from V1 to V5. Which one? V6 to V5. This one. Oh, is this one you're saying? V6 to V5? Oh, but okay, let's do it again. I think I'm making, yeah, that's right. Let's just do it. Yeah, that's the problem with it. Sorry, yeah. So let's just do it. Yeah, that's the thing. It's wrong. Yeah. So I'm sorry, this is not correct. Yeah. So let's just do it. So one come, let's first sort the edges. Okay, 1, 2, 2. Then we have 3, we have another 3. Ideally, I should be also writing the endpoints of the edges, E something, something, something. But yeah, this is 5, and then another 5, and then 7, and then 7. Let us also write a bit more. Okay. And if you're actually writing, you have to write it. Okay. So in any case, so this is, yeah, that's the good spot. Okay. Is this, and this is E17 maybe. This is E27. This is E76 and so on. Okay. So yeah, so first the 1 comes in, we draw it. Then the 2 comes in, you draw it. You take it. Then the next 2 comes in, you don't take it. Then 3 comes in, you take it. Then the next 3 comes in, yeah, you take this 3. Okay. Then the 5 comes in. No, this is this is the 3. You take this 3. Then the 5 comes in, you don't take this 5. Then the next 5 comes in, you take it. Then the 7 comes in, take it. Next 7, don't take it because it forms the cycle. Right. So this is surely correct. Yes. Thanks. Yeah. So it's very easy to go wrong. Okay, maybe it's not easy to go wrong, but I'm just making a mess. But it's a good idea to write it like this. This will also help you to think of a proof. I mean, yeah. So the very first step is sorting the edges, and I'm not going to discuss what's the best way to do that now. Okay, but this is an interesting question on its own. We'll see it later. This will our knowledge of a harmonic, not harmonic series, but that kind of recurrence that leads to logarithms will be useful, but we will not deal with it now. So yeah, so the edges are in this order, are in increasing order, and we select it. Okay, but why does this method work? That's the first thing. Why does this work? Well, I should actually just say that this is the first thing, because there is another issue with this, which I think one has to address, is, I mean, how do you, in an efficient way, check that it does not form a cycle with already selected edges? Yeah. So if some 100th edge is coming in and 99 edges you have already selected, how are you going to check, how are you going to check whether it forms a cycle or not? How will the computer know? I mean, you may make the computer store all the cycles that are already formed, but a new cycle, whether a new cycle is formed or not, how will the computer know? Okay, how how to know if a new cycle is formed? The first question is more important for us now, so let's do that, and then we'll also look at the second one briefly. How to know if a new cycle is formed? See, but this is not in some sense as laborious, maybe, or at least already it looks like it's not as bad as looking for all cycles, maybe. Okay, this is just when a new edge comes in, and you have to just check what cycles are formed from it. Okay, which involve it, because that's what we mean by new cycle, right? When a new edge comes in, and then you have to only look at what possible cycles are there containing it. So that's also pretty bad if you don't unless you write something more, but we'll discuss that. But these are the two questions we want to address. Yeah, so let's think about this. So any idea how we can show that this is the, now this looks like it's the best, but it's not, maybe, but it's not obvious, maybe, in the sense that it should be right, maybe, but how do we know? Because there's certainly a short-sighted approach. Yeah, we're only looking at each step, we're trying to do the best. Yep. So we want to show, okay, so we want to show that the resulting spanning tree. So I suppose that this is clear to everyone, right? That what we get is certainly a spanning tree. Okay, what we get is a connected graph, okay, which does not have any cycles. Yeah, that should be clear. If it's not clear, if it's totally unclear, please ask. Otherwise, try to prove it. Does anybody find this surprising, or like, don't know why it's true? Yeah, okay, because just at each step you're just preventing a cycle, but so eventually you will get a graph with no cycles, but it will have n-1 edges, right? And that is going to be a tree. Yeah, how? Yeah. Comparison. Okay. Okay, so let me then first write comparison. So let's say that, we pick, okay, say we pick the edges E1, E2 till En-1. Okay, we pick, and let's say some other process picks E1 prime, E2 prime, E3 prime, and En-1 prime. Okay, see, other process means that some other spanning tree, right? Some other spanning tree has these edges, and this is our spanning tree. Okay, yeah, now say, yeah. Mm-hmm. But why? In the sense that, okay, let's say that so obviously there can be commonalities between these two, right? This and this may have some lot of things in common, but the point is that, say that there is some ei prime, okay, and let's just call this t, and let's call this t prime, okay, some t prime. Say ei prime is in t prime but not in t. Okay, then you're saying that ei prime will form a cycle with when we put it in t. Even if it is not, it will still form a cycle, right? I mean that ei prime, ei prime is there, which is in t prime but not in t. Then when you put ei prime in t, it will form a cycle, right, with t, right? So t, I'll just use this language, ei prime has a cycle. Okay, let me also just draw it while before you say. So let's draw it here. Let's say that let's say this is L and M. maybe. Okay, so this is this Lth. Oh, God, 1 minute. Sorry. Yeah. Let us say this is L and this is M, and here we have a EI prime. Okay, and then see, this will certainly form a cycle. That's by the definition of a tree, that it has to form a cycle with T. I mean, if you put it in T, if you put that edge in T also. So these are already in T, form a cycle. And so this whole thing is T, and obviously there are more edges, more vertices and edges and so on. Okay, then what? I should also say this is EI prime. Okay, so basically there are two trees. We want to show that our tree does not have more weight. I'm not saying it has less weight than T prime, but all I'm saying is it does not have more weight than, all we are trying to show is that it does not have more weight than the tree T prime. Okay. Forms a cycle. When the cycle, so when T was being formed, these were getting picked. These got picked, but we did not pick this. Yeah, why didn't we pick it? And so on. Maybe you can use that reasoning. Yeah, so E prime is not in T. Okay, that is what I'm just saying. Yeah, those which are in T and T prime both, we don't need to worry about them. We can just sort of, they make our comparison easier. But the problem is, it's not so simple, right? Because I mean, EI prime did not have come after these edges were already there. Yeah, it may have come before these red edges were there, but it may be forming a cycle with something else. We do not know. Yeah, but we can write this phrase and we can think about it. Okay, EI prime, I mean, EI prime, let me just write this. It's the same thing, but I'm just writing it as a phrase. Okay, EI prime was not chosen in T. See, EI prime was certainly presented, okay, when T was being constructed, but it was not chosen. Now you can, why was it not chosen? It had more weight, and what more can you say? More weight, that's an incomplete. More weight than what? Yes, that's right. That's right. It must have been forming a cycle. Yeah, it must have been forming a cycle. Otherwise, it would have been picked. Yeah, that's because our algorithm is very simple. That's the beauty of having a simple statement, right? Yeah, so it was forming a cycle. So it was, one second. Oh, yeah, it was forming a cycle in T. Okay, it was maybe going to form a whatever it was. If I should rather say it would have formed a cycle. Yeah. Would have. So it didn't happen, but yeah, would have formed a cycle in T. So let us so now actually we can assume that the red edges came before EI prime came, right? Okay, so the red edges came before. So let's write that. So the red edges came before ei prime. The red edges that we can see. So you see, so now we have changed. So it's not, so we are saying that there will be some cycle which was being formed. Because just imagine if ei prime came among all the n, not n, but we don't know how many. So the graph G that we initially had, it can have many, many edges. Yeah. So then ei prime came and it was forming a cycle. And so that's why we did not pick it. But then what? Yeah. But you see, these things came before. These things came before. So they have lesser weight. So they don't have bigger weight. So don't have more weight than ei prime. So obviously to say they have lesser weight is wrong. I should say they don't have more weight than ei prime. Okay. But then what? Yeah. But that is not helping us to show, right? That is that helping us? Or maybe it is helping us. I think it is helping us, right? Because now it means that these red edges, all of them, none of them have bigger width than ei prime. So, and obviously all these red edges were not in t prime, are not in t prime. Is that right? All the red edges, I'm not writing this, all the red edges are not in t prime because ei prime is also in t prime, right? So there is some edge here which is not in t prime. Yeah. So let's say that there is a ek, okay, such that ek is not in t prime, right? So an ek does not have more weight. Ek does not have more weight. I should say weight of ei prime is at least weight of ek, right? Then what can you do? You can make this a member, and you can remove this. Right? And then what we have done? What we have done is we have taken the tree T. We have taken the tree T. We have added something from T prime, and we have removed something from T. Okay, so now this new tree does not have, so it's a spanning tree. It does not have more weight than T. Okay, but it is one step closer to T prime. Yeah, it's one step closer to T prime. You can continue like this and you can eventually reach T prime, and the weight would have not decreased. Okay, that's all I say. I think now you can write it. Even you don't need to write it also, but if you want, you should write it. Okay. So this way we can reach one step at a time. We can reach to T prime without decreasing the weight. Okay, please, if there are any questions, please ask. Also, if you see a flaw, please say. Maybe a flaw, can be, okay? Because it's not a proof that I remember. There is a proof, standard proof, which I know, but this is a proof that we have done. So I think it's better to. Seems correct to me. Okay. So any questions? Okay, if you want, you can have a look at it again later on, and please report if you see any flaw. It's possible, okay, because these are not very trivial statements and it can go wrong. So yeah, right. But this is the method. Okay, this is the method of the proof that is correct. should be correct. So yeah, so the word comparison was really the key. Okay, please, if you have any questions, you should ask. Okay, because we have class 1 week. So okay, so really, it's all about comparison. Okay, it's all about comparison, but we have also done something very unique: comparison and exchange. This exchange that we have done, right? This is again bringing us back to the thing that trees are structurally very simple. Okay, trees are structurally very simple, so they have a lot of exchanges, and they have a lot of variations. So there are many trees, and yeah, okay, that is the thing. And this exchange is really what is making things work. What was the exchange? Would anybody want to abstract? I mean, it's not abstractly. Would anybody want to isolate this exchange property that we have used? If someone can see it in that isolated way, it's very useful. Otherwise, I'll mention it as a theorem. It's also a theorem in Douglas West, the book. So, and by the way, as I said last time, I'm not following the book word by word because that we are not supposed to do that book. Okay. Point is that I'm just doing the interesting parts and also things from outside and so on, because it's an encyclopedia. It has so many definitions and such. You don't need to, it will take 1 year to do it completely. Yeah. So would anybody want to isolate this exchange property that we have kind of used? And I also mentioned it in the beginning. We are also used to prove something else earlier. So it's a very common theme. So really exchange is the thing. And it's like this, you see, if T1 and T2 are two trees, so you start with two trees, okay? Start with two trees, T1 and T2. So see, what are trees like? So tree is like what? So you have n vertices, right? And you have how many edges? So you have n vertices, yeah, and you have n choose two. I think by now all of us know this, obviously. N choose two. Well, this is n choose two. N choose two edges. Yeah. T1. See, if you can think of a tree or a graph in general as just a subset of these edges. Okay, just a subset of these edges. Okay, so T1 is basically a subset of these n choose two edges. Okay, if you call this set E, right, then T1 and T2 are essentially, more abstractly, these are just subsets of E, but they are special subsets. Okay, they are subsets which make a connected graph. Okay, but that's not very fundamental because connectedness does not generalize easily. Maybe it does. But point is that it is better to say that they are maximal graphs, or they are maximal subsets with no cycles. Yeah, that's what these are like. These are subsets of E which do not form any cycles. Yeah, these are subsets of E which with no cycles, but these are maximal members of maximal subsets of those kind. Okay, and that just captures everything, right? Maximal subsets with no cycles. That's what trees are. Okay, so you can look at trees as subsets of E. Okay, they're special family of subsets, a special collection of subsets which are maximal and they don't form trees. Don't form cycles. Okay, so see, subsets, but in general, if we forget about the term maximal, subsets that don't form cycles, okay, these subsets can also be called independent, subsets. Okay, now that if you think about it, that's not a very bad choice of name. Okay? Obviously in maths we choose the names wisely usually, so this is also called independent subsets, which is just name we are giving, but you'll see why we are giving this name. Maybe not now, but you'll eventually see it. Okay, sorry, these are called independent sets. Those subsets which whose collection of edges don't form a cycle. These are called independent sets. Why they're called independent? That's very, so not having a cycle means that, you cannot go from one place to the other in two ways. You can go from one place to the other in at most one way. Okay, which means that it's not like there are two different quantities which are equal, right? The two different quantities are not equal. Yeah, they don't depend on each other, right? Two different paths don't depend on each other. It's not like you can write one path in terms of, it's not like you can write one edge in terms of other edges, right? You can't write this edge in terms of other edges as sum of other edges. In some sense, you understand, right? That is the meaning of independent, right? One cannot be captured by the others. Here captured means forming a cycle, or no, I mean, here it means that one path cannot be written as sum of other paths. Okay, in a loose sense, right? That's what independent means here. Okay, all right. So that's what these trees are. Okay, and what we have shown is that all maximal subsets, all maximal independent subsets have the same size n-1, and the size really is capturing their behavior almost completely. Okay, right. But we had shown even the last time that this fact that all trees have the same size, or all maximal independent subsets, or all maximal subsets that don't form cycles, same things, they all have the same size. We had one way to prove them is using the exchange lemma. Okay, I'll just write the exchange lemma and not do the proof. That's just a repetition. So let me just write this very fundamental lemma, okay, which you can know, and you can use it in even in polynomials. You can use it in vector spaces. We will see. Okay, so if T1 and T2 are two trees, okay, and let's say E is in T1 but not in T2, okay, and you throw in this, okay, then there exists maybe I just say E2, there exists E1 in T1. No, in T2. So this is, sorry, so we are taking, no, sorry. We're taking something in T1, which is not in T2, and we are putting it in T2, okay? Now there is something in T2 that we can remove, that we can exchange, right? So we can throw that thing from, so you see, first we are bringing in anything which is there in T1 but not in T2, and we're putting it in T2, okay? Then we can take something in T2 which we can remove, okay? Which there will be something that we cannot completely, that there will be maybe unique thing, okay? Something in T2, okay? Such that that something you can remove, okay, is also a tree. Okay, so no cycles and so on. Now this is something that we've already seen. It's very simple to prove, but it's a very essential lemma to have. Okay, so remember, we are first adding something from the other tree, and then we are getting a bigger thing which has a cycle. Obviously, we can remove something which is not in the, obviously, which is not in, yeah, okay, which is in T2 but not in T1. Yeah, that's also, that can also be said. Okay, this is the thing. This is the exchange lemma, and this is a lemma which helped us to show that all maximal independent sets have the same size. Okay, all trees have the same size. Okay, but there is an exchange lemma in the opposite direction, which is also true, which is also something that we should just see, and that's also true. But that's something which we were confused about the last time. I mean, I was confused about the last time. So let me also state that. And that can also be used in reverse kind of processes where we go down at the, okay. So this is exchange lemma 1. So this is, I don't know the number. I think this 2.16 or something, but now we kind of see this inside out. So, okay, we don't need, yeah, so this is exchange lemma. Let me do one thing before we actually state the other one. 1 minute. Yeah, before we state the other one, let us just try to take, let's take a glimpse of this in some other place. Okay, so all of you would have seen some polynomials. Am I correct? Yeah. Okay. Okay. So let us consider some interesting thing here. Let us take the set. Yeah, let us see it here. Let us take the set of all 4-degree polynomials. That's all. So coefficients, real coefficients, it doesn't matter. That's not the point. Okay, that matters, but let's just take real coefficients. Okay. Reals, you can take rationals also. That will be the same. Set of all 4-degree polynomials. Okay. So obviously we understand what this is. This is just to write it. This is 4. These are real and so on. Okay. So we're taking a set of all 4-degree polynomials. Okay. So we want to understand, I should say that we want to understand the additive nature of this set. So remember, this set also has a multiplicative structure. You can multiply 2 polynomials, but then we will be going out of degree, right? So naturally, you can understand, I just want to look at 4-degree. Or maybe not even that, I should say, of all degree less than or equal to 4, I should say, okay? Because yeah, this can have degree less than 4 also, it can be, because when I add, it can go down, okay? So we want to understand the additive nature of this set, okay? So just so for the time being, let us just forget that it has a multiplication at all. That's helpful, okay? Otherwise, okay, that will help us to understand better. So now we want to see how many polynomials are needed, how many edges are needed, okay? How many polynomials are needed to generate all polynomials, okay? How many polynomials will be needed to get all the polynomials? Obviously, via addition. That's a very simple question, but let me write it. How many polynomials needed to get all of P? Let's call this P. Obviously, 5 is certainly one answer. Yeah, 5 certainly seems sufficient. Yeah, 5 is a maximum. See, there is no, yeah, that depends on usage of language. One can take 100 polynomials also, right? Yes, but yeah, maybe the way I've said it, need. Yeah, but yeah, it's the same thing. You want, yeah, I mean, I've not stated it clearly. I should say minimum kind of. So certainly 5 is, so let's write the answer clearly at least. 5 is enough. 5 is enough, and that is, you can take the constant polynomial, which is 1. Okay, so I also want to say additive nature of the set, and also we want to take multiplication. We also, it doesn't matter too much, but we should take multiplication by numbers. Okay, so see, we are not allowing multiplication of polynomials, but we can multiply by the numbers, by the real numbers. Okay, that we are allowing. Okay, then 5 is enough because we can take 1, and then as, yeah, we can take these are the canonical choice, but these are not always good for all purposes. That is why we have to study this subject. This expression is not always good. And this way to write polynomials is not always good. Just like, writing a number in base 10 is not always the best way to write it. Yeah, it's in the same way. So x cubed and x to the power 4, this is certainly 5, and this is enough. Okay, using these and adding and multiplying by real numbers, you can get all polynomials, right? That is clear. So we're not, so certainly we're not multiplying the polynomials. Otherwise, just one would be enough. Just x would be enough if you're allowed to multiply the polynomials also. But then that's a reverse kind of thing. Okay, then the higher degree you have, the worse it is. So 5 is enough. That is certainly true. Okay, so this 5 is certainly true. You see, these 5 are enough, and yeah, so the way I should say it is, yeah, so using these 5 edges, we are able to generate all the polynomials. Okay, but it is like a tree in the sense that, in a loose sense, that these 5 are independent. Why? Because you can write a polynomial using these 5 in a unique way, right? Any polynomial can be generated. Okay, so if you can go from any point to the other, or any path can be effectively generated, not generated, but effectively generated. Okay, between any two points you could go, generated in a unique way. So the unique way is important here. That's what gives it that, that minimal structure in a unique way. Okay, that basically is certainly true, right? I mean, a polynomial you cannot write in two different ways. Otherwise, yeah, so we know that 2x to the power 4 plus 3x cubed, it can never be equal to 3x to the power 4 plus 3x. Yeah, each coefficient has to match. That is in the definition of polynomials if you view it as an algebraic thing. Okay, but in any case, we know this. Yeah, polynomial coefficients are unique. I mean, that depends on how you define polynomials also, but in either ways it can be seen, yeah, that any polynomial can be generated in a unique way. Okay, so this way we call this as an independent set. Okay, now the real fun comes when, if I say, let's say that I take some other 5 polynomials and they also generate. One second. So I'll take some other 5 polynomials. Now, obviously, you guys can imagine there are many such polynomials, right? You could have also taken x plus, you could have also taken 1, you could have also taken 1, x plus 1, x plus 1 square, x plus 1 cube. That would have also worked. Okay, so let's say that, so this is what we can say is an independent set. It's a generating set and it is independent. Independent is not so important here, generating is important. Okay, let's say, so the point is it can be written in a unique way. Okay, now let's say that p1x, so let's make it a little more interesting, or let's not like this. Let's say that f1x, f2x, f3, let me write x, because not all of us are experts in polynomials. Okay, so let's write this. Let's say that these are, say these also generate p. Okay, now you see that can happen, right? You could have some other polynomials which also generate. Okay, you can have all kinds of polynomials, all kinds of families. So let's say there are some other 5 families, and a very simple example is you can just take, you can just take x square, x cube, x to the power 4, x to the power 5, x to the power 6. No, till x to the power 5. Yeah, this you, wait a minute. Am I correct? Yes, right. This, no. Wait, I make some mistake. this should certainly work. Okay, my theory says that this should certainly work, but this is, yeah, someone has a message. Yes, okay, sure. Yes, I'll do it. Yeah, sure. So will these 5 polynomials also generate all the polynomials? Yes, right? They will. So let's first answer that question. Yeah. Do these 5 polynomials also generate all polynomials? Can we use these to get all polynomials? Means, is this statement correct? So let me just put a question mark here. Then we can go into the hmm? Oh, sorry. No, if you take x plus 1, no. But independent here means that you cannot write. So independent here just means that you cannot write a polynomial in 2 different ways using these things. Right. Yeah. Independent just means that, yeah, you cannot have some combination this side equal to some combination this side, unless they are identically the same. Unless they are term by term same, you cannot have it. Yeah. So that's certainly, and when my question here was completely off, sorry. That is just the word independent we are using, just in the same sense as in trees. They are in some sense independent, they don't have cycles. Okay, I mean, cycles means cycling back, right? That is the word. But here that's completely wrong. I mean, we can't have x to the power 5, we are looking at x to the power 4. So maybe let me take something else. So yeah, let me see, then it becomes very simple though, because they're all simple from this. Yeah, will these polynomials generate everything? Surely. Yeah, because you can get 1, you can subtract this from this and you can get 1, and then you can get everything, right? So from these 5 polynomials, you can subtract 1 plus x squared from x squared, you can get a 1, and we are allowed to subtract. So when I say add, I mean I'm allowed to subtract also. Or you can say multiply by -1 simply. Okay. This, you get a 1. Once you get a 1, you see you get everything because you have x squared and everything. Okay. So yeah, it's also generated. Okay. But there could be many other non-obvious. Point is that there could be many other non-obvious sets which also do the same thing. And in higher degrees, it also becomes interesting. Okay. So let's say that there are 5 polynomials which also generate P. Okay. So this is one generating set. This is one connected graph, one tree. This is another generating set, another connected graph, another tree. Okay. Now, what I'm going to do is, let's say that I take these 5 polynomials which generate all the polynomials, and I take one polynomial from the second. So let's call this second graph, right? Second set. Let's call this G2, generating set 2. Okay, I'll take f1x. Okay, so this is like adding the edge from the other tree. Okay, now can we do what we did for trees? Meaning that, can we claim, so now we have this, right? Now can we remove something from this set and still keep it a generating set? That is the question. Right? Does everybody understand this? Yeah. We want to see if we can remove something. I've added something, right? Now, can I remove something from the original set? Something from 1x, x square, x cube, x to the power 4. Can I remove something, and so that the resulting set is still capable of generating everything, so that the resulting set is still a connected graph in graph theory? Can we do that? Yeah. So basically, I'm saying that can F1 replace the role of something else? Of some edge, some polynomial that's already there? And the answer is yes. But these are polynomials. These are polynomials. In what sense are greater? Okay, no. But this is simpler than the weights thing. And the weights thing actually was more complicated. It's actually much simpler. Okay. It is not. So it's the fact is true, but the method may be slightly different. Okay. But it's very simple. Can anybody, those who have done more of polynomials, it should be simple to them. Can we remove something from x1, x2, x3, x4 so that so can we delete something? And you understand what I'm trying to do? I'm trying to delete and still keep it a generating set. But the highest, yes, right. Just take any degree, anything that's there in F1, and you can delete that monomial actually. Okay, so yeah, that's right. I mean, see, in the end of the day, F1 is also a 4-degree or 3-degree or 2-degree polynomial, not more than that, right? So it's so F1 is also like this. Yeah, F1 is something like this. Now the point is that one of these AIs is non-zero. It's non-zero, so that's everything here is non-zero. Okay, these are non-zero. Otherwise, it will not. Otherwise, it will not even happen. But I should still just say, yeah. So it is very simple, right? So just, I mean, at least one of AI is not zero. Okay, let's say, for example, that A3 is not zero. Okay, let's say that A3, for example, was 5. I mean, you can just take some arbitrary thing here just for explanation, but you can understand. Yeah, it is it is a non-zero-ness to begin with. Okay, so it could be 5, it could be 100, it could be 20 factorial, it could be 1, it could not, there may not be any constant. Okay, yeah, and it doesn't have to be a 4-degree polynomial, just to say. So it could just be like this. Okay, and then you see, because 100 is there, 100 is non-zero, so that's the first step. Okay, then you see f1x can now, f1x in collaboration with x cube and x square can replace the role of x, right? f1x in collaboration with x cube and x square, it can replace, so whatever x was doing, now these things can do that. Right? So now you can understand that x is no more needed. I mean, we could have replaced x cube also, right? But x is no more needed. It's very clear. Any polynomial, you write it using these things, but then you can replace the x by this. And then it's written in terms of, it's written without x using the other things, using these 4 things. Is that okay? Yeah. Just, you can take an example. Let's just say you want to write the polynomial 2x plus 3. Simple. Now, what you can do is you can replace what? Simple, right? You can replace x by this. And you see, now you have just used the constant, that is 1 times 3. You have used x squared, so it should be, basically I should circle the 1, but you can understand. Yeah, so then you can use the 1, you can use the x squared, you can use the x cube, you can use f1x, you can use x to the power 4. Didn't need to here, but you can write 2x plus 3. Okay, so it's very clear, right? And you see this can be done. So it's very clear this can be done. Okay, and this is what we did for trees. Right? This is what we did for trees also. So is there any question? Okay, so what we have shown is something, in fact, something non-trivial, though we have shown it in a playful, I mean, if one would state it as lemmas, that the dimension of the space of 4-degree polynomials is 5. Let's prove that claim. Then maybe it's a little, okay, but this seems pretty obvious stuff, right? So this basically means that if you, you can chip in anything and you can remove something, okay? This is precisely what we did for trees, okay? And what is the consequence of this, you may ask? Can anybody think of a consequence of such a statement very similar to what we have proved for trees? What is the consequence of such things? And remember, you could have done this with any set, so you don't have to even start with this. You could have started with some set of polynomials, g1, g2, g3, g4. So, I mean, I should write x, but yeah. And I could have done the same thing, okay? So this is g1. So I should say from g5 maybe g5 here. Sorry. No. So my point is that this is very general, but just the proof is the same. It's the same thing, right? So the point is that from g1, I could have removed some gi, and I could have added some fj, and this is still a generating set. And remember, I'm saying that you first remove some gi, and then there will be some fj that you can add so that it's still a generating set. So that it will still generate. Forget about independence for the time being. We're just looking at connectedness, maybe you could say. Okay, just still a generating set. Okay. So what have we shown in this way? What did we show for trees? We showed that the minimum connected graph has size n-1, right? So here we have shown that smallest generating set has size 5. You can just do the same proof. You can just, because you know one set which has 5, the path, the 1 plus x square plus x cube, the 1 comma x comma x, that's it, right? You can use that and you can do this comparison. You can show that the smallest is 5. Yeah. Because certainly you see that 1x x square x cube and so on, that's minimal, right? You can't remove anything from here, like solely, I mean, you have this set, right? This is certainly the smallest. It's independent, generating smallest. You can't remove anything from here and still generate everything. That's impossible. That's very clear. So you can hold on to this minimal, and then you can show that every other generating set that claims itself to be the smallest has to be of size 5. Okay, so we have shown that 4 polynomials can never be used to generate all 4-degree polynomials. You need at least 5 polynomials. Okay, but actually this is nothing. We have shown much more actually. We have shown much more. Just like we said that to form a tree, you just need to make sure you don't form a cycle. Yeah, we showed that to make a tree, you just need to ensure you don't form a cycle. Okay, here also, so we have just said that to form a tree, you just make sure that at each step you don't form a cycle, right? And you just keep doing it. Okay, here also we just need to make sure that the polynomials you keep putting in the set, they don't collect, I mean, they don't have a relation among them. Okay, and then any 5 polynomials you take will do it. Okay, but let me have not said that clearly. Let us just collect what we already have. Yeah. So using this, the consequence is that smallest generating set, size 5. So smallest generating set has size 5. And now, now we want to generate generating sets. We want to create trees. Yeah, we want to understand how we can create trees. Okay, how we can find, like when I'm handed over 5 polynomials, how to decide if they generate everything or not. Okay. For example, I mean, obviously not all 5 polynomials will work, right? If you take x plus x square, x cube, s to the power 4 and 1. Sorry, 1, 2, 3, 4, 5, 6. No, I mean, you can, yeah, this. You see, it will certainly not work, right? It will not work because I've wasted things here. I formed a cycle. I have a relation in this. Yeah, these 3 are, you can add the first and third to get the second. Yeah, so not all 5 will work. Okay, so 1 second. Yeah, yes. So let me, yeah. So any maximal set of polynomials which don't have any relations, which don't form a cycle, don't have any relations, will generate all, will be connected. This is not very difficult. Now, what do I mean by don't have any relations? Okay, don't have any relations. I mean, I've already told you they don't form any cycles, but that just means that you cannot write one in, for example, if these 5 are there, right, then I should not be able to write it as, I should not be able to do this, something like this, and then this cannot be equal to f4x. Means you cannot relate any, you cannot write an equation in this form, right? So you cannot write one thing in 2 different ways. You cannot go from one point to another in 2 different ways. Okay, that is what I mean by don't have any relation. Okay, relation means that a relation, an equation, a form of an equation, right? So I don't want any equations. Okay, so as long as you do not want any, as long as you do not create any equations among your polynomials, okay, and as long as you don't create any equations, you don't create any cycles, okay, don't have any relations, same thing. Okay, as long as you don't do that, okay, then you'll end up with a maximal generating set. You'll end up with a generating set. Okay, once you cannot do it further. Okay, so what does it mean? It means that you can start with any polynomial, start with any edge. Yeah, start with any polynomial f1, and I should just say maybe some different thing. Okay, start with any polynomial q1x. That could be anything. I mean, a 4-degree polynomial. It could be any 4-degree polynomial. Okay, it could be any 4-degree polynomial. You could start with x choose 3, x into x minus 1 into x minus 2 by 3 factorial. You can write it like that. Right? So you can start with x choose 3. You can start with any polynomial. Okay, start with any polynomial, and then just add a next edge, but just make sure that they don't have any equation between them. So you cannot write 5 times q1x is q2x. No. Okay, don't have any equations, don't write something in 2 different ways. Okay, as long as you don't do that, and then you add the third one, but then again you have to just ensure that truth, that you don't create a cycle, don't waste anything. Just add a polynomial which does something new. Yeah, add a polynomial which does something new. That doesn't, so don't add a polynomial which already does what these 2 things do. Okay, that does something new. That's what it means, right? Not forming an equation. And in this way, if you continue, then eventually, and if you reach a maximal, let's say, and if this is maximal, yeah, meaning that no more can be added, no more can be added. Okay, so you have, what have you done? You have started with an edge, started with a polynomial, you have added edges so that they don't form cycles, you have added polynomials so that there are no relations. Okay, and you're just doing this short-sightedly and just adding polynomials. If you keep doing this, just make sure that you don't create any equations. And when you cannot do it anymore, how would you know you cannot do it anymore? Well, one answer is we will see that once you've reached the size 5, because we'll show all of them have size 5. That's what we want to show. That's the key. That's the key. But let's say you somehow know that you cannot add any more. Then what you get is a connected graph, or what you get is a generating set. These 10 will generate everything. And that is, can anybody say why that is true? That is maybe not completely trivial, but once you see it, so once I'm stuck here, that I cannot add any more polynomials, then my point is that then these will generate all polynomials, meaning that I can write any other polynomial using these. Yeah. So no, but actually it will never go till infinity. Okay, it will stop somewhere. No. So we actually don't know, but see, each of these are less than degree 4. That is our initial. So I didn't say that, right? Everything is coming from P. Okay, I mean every edge is coming from the graph. I can't take edges from outside the graph, outside the endpoints, right? So everything is coming from these only. Okay, but what I'm doing is I'm trying to, so see what we have seen. We have seen that if you want to generate all 4-degree polynomials, then you will need 5. You cannot do less than that. Okay, that was somewhat clear, but not didn't have a proof. Now we have a proof. Okay, I mean you could have still proven it by some other ways, but we have seen now. Okay, by this exchange method, in the same way as all trees have at least size n-1, this will also work. Okay, n-5 you will need by this exchange, because I already said as 1x square is there, you can compare with that and you can do exchange and show. But now we want to ask the question, how do you generate trees? Okay, how do you find a set of polynomials, or given a set of polynomials, how do you decide if they generate all the polynomials, all of these P? Okay, so obviously these are inside P. Okay, so what am I doing here? I'm saying that just do what you did for graphs. Okay, you start with a polynomial q1x, which is, let's say, x choose 3. This is what I mean is that x minus 1, x minus 2 by 6. Any polynomial you start with. Okay, and then just keep adding polynomials, and these polynomials are all coming from this set. That is important. We cannot go outside the set. Okay, but the only condition is that at each step, make sure you don't form a cycle. Make sure that there are no relations. So there are no equations between these things. One cannot be written using the others, and that is a natural thing, right? If you want to generate everything as quickly as you want without any relations, you don't want to keep generating what is already generated. You want something new, right? That is what we are doing here. Okay, and you do this and you keep doing this. Okay, let's say that there comes a time when you cannot do it anymore, which is what is meant by maximal. Yeah, then the claim is that this set will generate everything else in P. But that is in the definition. Yeah? If you take anything else, if qx is some polynomial in P, yeah, then qx can be written using these. Why? Because because we cannot add qx in this set. Yeah, you cannot add qx in the set because nothing can be added. Nothing can be put in the set, right? If you add qx in the set, so if qx is thrown inside S, then there will be a relation. There will be a relation between them. Is that right? Yeah, there will be a relation between them. There will be something like, I'm just doing something loose here, but 100 times QX plus 2 times Q1X and so on, right? There will be a relation. But if there'll be a relation, that's the problem. And then there'll be some other Q2X, something, right? There'll be a relation between the polynomials, set of polynomials, right? But then you can write the Q1X, you can put everything to one side, right? You can write Q1 using the others. That's it. That's what we wanted to show, yeah? So because you cannot add anymore is exactly the same as saying that you have generated everything. It means using these, you can generate everything. So you cannot throw in anything else. Okay, so this is just like trees. Okay, just like trees, maximal set of polynomials don't have any relations. Okay, any maximal set of polynomials which don't have any relations will generate everything. That's obvious. This is not a very difficult statement. Now, just like we have proved for trees that every maximal set, which doesn't have any cycles, will have size n minus 1. Here also, in the same exchange way, you can show that it will have size 5. Meaning that this will stop at 5. So the claim again is that this will not go to 10, but this will stop at 5. Everything will stop at 5, exactly at 5. Okay, so here is the claim. Just like for graphs, all maximal independent sets or maximal sets with no relations, in which the polynomials don't have any relations between them, with no relations, have same size. And the fact that they have size 5 is clear because 1x square again is a prototypical example. Yeah. And this is again by the same exchange argument. You take two maximal sets and you do that exchange argument. You will show that one of them has size at least as much as the other, and then the other way you can show. Okay, I will continue this the next time. Okay, meanwhile, you guys can think about this. Let's review this again and continue this the next time. Meanwhile, let me go back to the trees. Okay, but just take a minute and just think if you have any questions. But you can see the connection. You can see how connected, and this will be a very non-trivial statement. It's saying that any 5 polynomials which don't have any relations will generate all polynomials of degree 5. That will be the consequence in the end. Okay, and that's the first theorem in linear algebra. Okay, you'll see more, but I'm doing it in a slightly different way. This is not there in Douglas West. You can see the connection. You can see how similar the flavors are, and on some level of abstraction, they are the same things. Okay, if you remove the algebraic structure, well, the reasons why they have some things are happening, I mean, the intrinsic reasons may be different, but they can all be written under one common language. That is the key, and that is the key, right? It's having one common language to describe different things. Okay, please ask any questions, any simple questions, difficult questions I can try to answer also, but simple questions more so, please ask. Okay, would anybody want to summarize what we have done? That's right. That is certainly that's the main part. Yeah. So we have taken not one, but we have taken the set of all 4-degree polynomials. Yeah, all 4-degree polynomials, and we have said that if you want to generate them by addition and by multiplication by numbers, not of the polynomials, then 5 are necessary. You cannot do with less than 5. Okay, and that's just the exchange argument. But you have to still write. You have to still take two sets. You have to take the standard set 1x square and the other, and to compare and so on. You have to write. I've not done that, but that is the first thing. These things can also be done by matrices and determinants. That's a computational approach to linear algebra, but we are not doing that now, obviously. Okay. The second thing, which is a very non-trivial thing, okay, in some sense, very useful thing, and somewhat surprising maybe, is that any polynomial, any five polynomials you take, as long as there are no equations between them, as long as they are truly different polynomials, they will generate everything. All maximal sets with no relations have size 5, and they will generate everything. And my claim is that the proof is exactly the same as we do for trees, but I will still do it the next time. For some, it may be easy, but we'll do it. And then for those who are easy, I'll mention a third, fourth place where you can use this theory. Okay. So this is, I think, very interesting. Okay. Yeah. This is what is called, it's not actually linear algebra, is not this. The way we are looking at it is called Matroid theory. Okay. Matroid, this is called Matroid theory. It will be, if you try to read it, it might be a little out of reach for the time being because it's very abstract. Okay. But yeah, I mean, I studied this in college, but later I realized that over the days I'm realizing, I should say, that this can be said in this simple way. Okay. And so many questions about, I've seen some Putnam questions, they become so easy. Not so easy, but they become, I mean, you can actually see through the questions if you kind of understand this. This is basically an abstract study of independence. Okay, that the minimal nature of independence and abstracted. Okay, and this is the way mathematics runs. Okay, this is the way topology is an abstract study of, sense of closeness and distance, and like that. Okay, so now, yeah. So there was the other exchange lemma which I could have shown in that context also, but let me just do it for trees now. Let's not go more into that polynomial thing today. Okay, the other, and this I will not prove, you should try to prove it. Okay, otherwise then the other, but this is also easy. The other, it's not equally easy maybe, but it's also easy. Let's see the other exchange lemma. This can be very useful. So at first I used to think this is not possible, so I was being very stupid. I took like 15 minutes to find a proof. But then when I was looking at it today, just to review what I have to say, I just saw it in a second almost. So maybe that time I was being stupid. So it can happen. The other exchange lemma is just in the other direction. Okay. So that was addition, deletion. This is deletion, addition. Deletion, addition. Okay. So here you first delete. Okay. So once again, you have two trees. I was a little surprised at this also. I don't know why, but now I clearly see that there's nothing surprising about it. You have two trees, T1 and T2. Once again, all the usual things are there. And here we don't need any weights and such. Okay, so this is just a simple thing. But as we saw, it was used in, by the way, the algorithm that we didn't go to the second question of it. That algorithm which Chandan suggested, it comes in the name of what is called Prim's algorithm. Okay, so what we did, you can go back and look at it again if you need to, but it's called Prim's algorithm. Okay, just saying because you can then, if you want to read more about it, you can see. Okay, you can try it out. It's what it's called. But usually the theory is, and we don't need more than this, becomes very specific to the subject. Okay, it's called Prim's algorithm. Yeah. Okay. So let's move on. Yeah. So then this is the other lemma. So here what we are trying to say is that if if E1 is in T1 and it is not in T2, okay, remove let, okay, remove E1. Okay, now we are saying that we can find Okay, we can find something from E2, from T2. We can find an E2 in T2. Okay, this looks stronger, huh? Such that so there was an excess and we were able to remove it. This is the other way. And this further reinforces the point that trees are structurally very simple. All the edges of a tree are sort of the same, have the same features, or as far as their contribution to connectedness is concerned. Obviously, they have different degrees and their leaves and they have different heights and other discriminations can be put. But other than that, I mean, in the sense of connectedness, all of them are kind of playing the same role. They're structurally very simple. Just like the set of all polynomials of degree 4, they're structurally very simple. They're described by one number, that is 5. Just number 5. The number 5 is what's describing them. Yeah, because you just need 5 coefficients, 5-dimensional vector. They just have that simple structure. Okay, that's why that's one number that the dimension is enough for them. Okay, just there's something similar here. They have some sort of simplicity, and that's why they come in large quantities, because they can be easily created. Okay, n to the power n-2. Even for polynomials, we can ask how many of them are there, or rather how many generating, how many minimal generating sets of polynomials are there. But it will be infinite if we look at reals. So for that, we have to see something else to make it finite, and then interesting counting questions come. But we'll see that later. So we have this. So we can find the E2 in E2 such that, yeah, so that we can make the situation good again. So that we can, so we have removed the E1, and then we can add is again a tree. Okay, please try to prove this. Okay, please try to prove this. Okay. Note it down. Okay, just give me 2 minutes, then 1 minute also, some water. Okay. All right. So let us now move to the next. If just, I mean, in the simple case, you can just draw some pictures, make 2 trees, try to remove one edge and see if you can make it up. Do this for different edges. You can then try to understand why are you able to create a tree. Right. The next thing that we do will also make this lemma more kind of, will help you, guide you in the proof if you need to, is, I mean, how to, so there was second aspect, right? Sorry, of the algorithm is how to, so really the question is that when EI is added in our algorithm, maybe now I can use the word Prim's algorithm, but really someone just said it, right? Chandan said it. So it's, you see, it's not a surprising algorithm. Okay, the time in which this was made, maybe it was a little hard because of notation and such, but now we have repeatedly seen this greedy phenomena work out in trees, so it's not a surprise that it does work. But in any case, when EI is added in Prim's algorithm, or the greedy algorithm rather, is greedy, is a greedy algorithm. There are others also. Okay, for this particular thing, added in Prim's algorithm, then how to check if a new cycle is formed or not. So I should rephrase, I should not say added when Prim algorithm, when EI is presented, right? When it comes in the queue, Are we going to check all neighbors of EI and then how are we going to, what should you do? How should you track things? Is the question. So let's say EI came. Let's say this V1, V2. Oh no, that's not, can be misleading. Sorry, this VKVL. Yeah, think about this. This can be given in some other ways, but just putting it like this simply. 1 minute, I'm just looking for my phone. Yeah. Okay. Oh, 1 minute, I'll just come. Yes, right. This, and we had discussed this kind of thing when we were trying to have, when we were trying to say that, you try to create a tree by not adding cycles, by not creating cycles, then there was some feature. When cycles are not created, if you add an edge and cycles are not created, then something special happens. So when I'm adding an edge and no cycle is getting created, then ask yourself what happens. What is it that is not create, that is making it not create any cycle? So you see, no cycles are getting created because it means that before this means, so if, let's write it, right? So if no cycle is created, yeah, so it means that VK and VL, yeah, were in different components. Yeah, they were in different, they were in different components. That is a key. Think about this, right? This and this were two different blocks. Now, obviously, there might have been there may be more blocks. I'm not claiming that, but they were in different blocks. There was no path already. That is the whole point, right? If there was a path, then why would I add this EI, right? So EI added and no cycle was getting created, which it means that EI was the only way to connect VK and VL. Okay, it's a cut. It's a cut between. It's a bridge between VK and VL. Okay, if it was not there, then there would be no connection between them. Okay, so the component of VK, meaning that the connected part, the part of the graph that is connected with VK, and the part of the graph that's connected with VL, they are completely different before it came in. Okay, so basically the graph, the number of pieces that the graph was in has reduced by 1. The number of components reduced by 1. I could have put it like that. Okay, and this we have already said earlier, right? The number of pieces, the number of components reduced by 1. The number of pieces reduced by 1, and that is what we can use to design what we can say a data structure. Okay, but don't need to say it in that terms. Okay, what I can say is that initially what you can do, you can dynamically So you can dynamically keep something which is initially you can just keep all the vertices separately. Okay. Initially, you can keep all the vertices separately like this, because initially your graph has n pieces, right? Initially, it's just n vertices. So now I'm describing a process which involves a dynamic update, which you have to do so that whenever you add an edge, it will be easy for you to check whether a cycle is formed or not. And for that, we are using this dynamic storage thing. At the same time, though, more importantly, we are using this mathematical property that no cycle being formed means that two worlds are coming together, right? Two components are getting combined into one component. Okay, the number of components is reducing. Okay, and that's if and only if the number of components are not reducing, it means that you have created a cycle, right? I mean, something was already connected and you put another edge in that. Okay, so something like so moves on and on like this. So first you can just keep it like this. Maybe I should not say 1 2 3. It doesn't matter. This is also as a pack library is there. It's called, I think, disjoint union, something like that, which you can just invoke and it will automatically do these things. Okay, but I'm not too much interested in that. I'm not interested in that at all. But this and things. Yeah. Now see, every time you add an edge, so every time an edge is presented, yeah, when edge EI is presented, you know then that VK and VL are presented. This is the thing, right? Then all you need to see is if VK and VL are, so here they are different, right? So maybe I should like this. So initially you are like this, and you have these edges, E1, E2, E3, En. Okay. Now remember, this does not mean, so E1 does not mean V1, V2. It could mean V5, V6. Yeah. E2 could mean V2, V9, and so on. You don't know. So when E1 comes in, E1 is the smallest rate. Now what do you do is you take the union of these two pieces, V5 and V6. Okay. So then, so here you have V5, V6 all separate, right? But when E1 comes in, you combine this. So you take the union. Okay. You take the union and then you keep the rest as they are. Okay. And so you understand what to do, right? When a new thing comes in, when a new edge, let's say E2 comes in, right? Then you'll combine V2 and V9, right? And those things that you're combining into one set, they are one connected component, right? So when a new edge EI comes in, it has its VK, VL. You need to just look at these pieces. They will be less than n, so not too much to look. And it will just see if VK and VL are in different pieces. If they are in different pieces, then if I take the union, it means that they were in different components. So you're not going to create a cycle. But if they were already in the same piece, added sometime together somehow, indirectly created a path, taken the union, right? Then they form a cycle. Yeah, is that okay? Yeah, it's basically just keeping track of the pieces, not pictorially, but like this in the form of data structure, right? It's just that it's a simple thing that whether you're joining two components or not, and I'm just keeping track of what the components are in this phase. See, there could be many cycles in a graph, okay, but there cannot be too many components in a graph, right? The components can be at most n. Okay, there can be at most 10 components, and they keep going down. So that's it. It's just a simple way to keep track of things. And yeah, at the heart of it is this thing that if no cycle is created, it just means that you are two different components are getting conjoined, and that you're just writing it like this. Okay. So any questions? Yeah. This thing, right? Okay. So let me show it in the case of a graph. Yeah. But you understand this, right? That if no cycle is getting created, it means that um, the endpoints of the edges were in different components. Yeah. This mathematical fact is clear. Okay. So then it's very easy. Then this is the main thing. Now, if you see, if what we can do is we can just take a small example. Yeah, let's just take this. Now, can yeah. So let us just keep take the simple graph, and let us just imagine that all the weights are 1, because the weights are not important here. Okay, or maybe because the order simple. Let's say this. Okay, so and let's say that we have this ordering. So we have E1. Let's say that is V1, V2. Then you have E2. Let us say, or let me not write it here. Let's just E1, E2, E3, E4, 5, 6, E7. All have weight 1. Okay. All have. Okay. Now, we are basically just going to keep track of the components. Okay. So we will dynamically keep track of the components. Okay. Initially, what are the components? So if you initialize it, yeah, initially, what is the situation? Yeah. Initially, the components are just pieces, right? Nothing else has been, nothing has been put in yet. Everything is just there, just lying there, right? Now, let's say that the vertices, let's say the edges are ordered in the usual way. Let's say they come in like this. E4, E5, E6. They come in like this, right? Now, when E1 comes in, E1 walks in, what it does, it takes the union of its endpoints. It takes the union of the sets which have the endpoints. Okay. And then your structure becomes this. At this, after the first step. After initializing and then taking the first step, this is what you get. Okay. Now, we will have to net. This is, yeah. Now it's, now when E2 comes in, nothing happens. No, I mean, again, no cycle is getting created, right? So this step 3, E2 walks in, E2 comes in, E2 connects V1 and V3. So what do? I take the union of these 3. So I'll take the endpoints of E2, right? And I'll join the 2 sets, okay? Which means basically that I'll just combine the 2 components, which is exactly what is happening, right? It's combining the 2 components. Now I'm just writing it like this, okay? Now E3 comes in, and E3 is between V1 and V6. So at this stage, I will have to combine V1, V2, V3, V6. Okay, and in this way it goes on, right? Now when E4 comes in, yeah, when E4 comes in, you see it creates a cycle. And how, see, you can see that from the graph, but you don't want to be seeing that from the graph, okay? E4 ka definition, see the definition of E4. E4 definition is V3, V6. Forget that you can see it in this graph. You can see it, it's clear, but if it's a big graph, maybe you cannot. The point is that we want to see it in this way, okay? So V3, V6 comes in, sorry, E4 comes in, then you have to look at V3 and V6. Oh, but V3 and V6 are already in the same component. And this is how you check that that a cycle is created. This says that a cycle is created because things are already in the same component and you're putting an edge. Okay. So here there'll be an alert, cycle is created, don't take that edge. See, in a very simple way, we didn't have to actually look for the cycle. It was just from here that the robot could see. There's no need to look at all cycles and check everything. No exhaustive check is needed. It's through a property of, when cycles are added, something interesting. When a cycle is created, it means something that can be tracked easily. That's the magic of it. Okay. This way you can continue. Okay. So I suppose, yeah, there is a thing. Okay, so that's what it is. So next I want to talk about cuts. Okay. Yes. Yes. So you see, E4 comes in, nothing happens. Yeah. Okay. Right. So the next thing I want to do is about cuts, but let's leave it. Let's not do it today. I think it's already, yeah, too much, and it's a new topic. So should we? Yeah, no. Let's just like this. We can review what we had done, right? Cuts. Then we can at least I can put the question. Yeah. So we were looking at cut. Okay, cut edges. If I have to say, cut edges is just cut edge. Okay, what is a cut edge? So basically, a cut edge is an edge whose removal disconnects the graph. So it's a very important property, very important, I should say, edge. In later on, it will become a set to look at. Okay, an edge whose removal disconnects the graph. Okay, means that breaks it up. So obviously a cut edge is just an edge which is not on a cycle. That's the same thing, right? An edge on no cycle. It is something that does not belong to any cycle. That is exactly what a cut edge is. It's the same thing, right? It's the same thing. Yeah. So what can we say about cut edges and trees? Can anybody say? Cut edge and trees. What is the connection? Yes, exactly. And that can also be taken as the definition of a tree. Yeah, because if every edge is a cut edge, it means that it's a connected graph, but there are no cycles, and there's a tree. It's the same thing. Okay, so it's the definition of, so one we get another definition of trees. Okay, so that can be a simple. Yeah, so I'm not writing it. That is very simple. Yeah, so cut edges are okay for the time being. We don't want to say more than that. Some graphs don't have any cut edges. Yeah, sometimes you don't have any cut edges, and then you have to look at the smallest number of edges that's called edge connectivity. We'll talk about that later. But what we were talking about is cut vertices, cut vertex. Okay, this is again a vertex whose removal disconnects the graph. Yeah, let me write it separately. A vertex. Yeah, so today I couldn't get to the problems, but surely next time we'll start with that. Removal disconnects. Okay. Yeah, this is fine. Yeah, removal disconnects the graph. Okay. So this we had seen. So we had seen that leaves are not cut vertices. Yeah. Leaves are leaves are not cut vertices. It's what you have already seen. Yeah, if you remove leaves from a tree, leaves meaning degree 1 vertices, which have only one neighbor, one parent, that's all. They are not cut. This is called no cut vertices also. And the second more important thing is, okay, maybe I didn't say this, so you guys should think about this, okay? Every graph now I'm saying, last time we did a variation of this, which we just use spanning tree and so on, but now every graph has at least two no cut, two vertices which are not cut vertices. So we are not saying you remove them together. No, that's a different thing, okay? We are just, that might also work. But the point here is that these two are separately, they're not cut. If you remove first one of them, doesn't disconnect the graph from the original graph. Now from the original graph, if you remove this other one, does not disconnect. Okay, that's all we are saying. It does not cut the graph. Okay, every graph has at least two cut vertices. Prove this is very simple. Note it down and prove it. Okay, but the third thing was that graph has exactly two no cut vertices means it is a, any guesses? If it has exactly two vertices which are not cut vertices, then what is that graph? It's a path. This we have not proved. Paths, a path obviously has this property. Okay, if you take a path, then obviously it has exactly two vertices which are not cut vertices. Yeah. This is a cut vertex. If I remove it, the graph gets disconnected. So it is a cut vertex. The endpoints are, as has been the flavor of no cut vertices, the endpoints are no cut vertices. Endpoints are no cut vertices. Okay. So obviously there are no others. So in a path, the other way the statement is trivial. Okay, the path has exactly two no cut vertices. But this is the harder part, structural graph theory. It's not that difficult either, but this is what I'd asked at some point maybe, but I put everything in one context, so you can try to prove this. A graph that has exactly no two cut vertices has to be a path. Okay, it has to be a path. Think about this. Okay, we will do this the next time. Okay, any questions? Mm-hmm. No, but here we are only removing the vertices. So here we are not thinking of removing the edges. If you're asking for removing the edges, then that's a different question. If you remove the edges, you remove the edges. You don't remove the vertices, right? If you say an edge, so then this edge, yeah, because this is also a tree, so every edge will be a cut edge, and that's easy to see also. Yeah, so that is the thing. So this is a very simple thing, but this is a statement that you want to show. Okay, but the next time what we want to do is something more interesting. You see, when you have a tree, yeah, when you make a tree, we'll prove these things, but when you make a tree, and so obviously we have said that in a tree, when you remove an edge, it gets disconnected. But what happens when you remove a vertex? If you have a tree and you remove a vertex, then what happens? Yeah, if the vertex is a leaf, then nothing happens. Means that it doesn't get disconnected. But if you remove a vertex like this, a highly responsible vertex, If we remove the vertex, then what happens? How many components are created? And how can we make sure that the components that are created have roughly are not too lopsided, they're roughly equal? How equal sized can we make them? So these are very interesting questions. Okay, and we'll see some applications of this also. Okay, balancing and so on. Okay, so yeah, so we have described cut edges, we have described the relation between cut edges and trees, and then this is some problems to try. But then next time we will trees and cut vertices. We'll try to see what happens when you, yeah, when you do that. Okay. Okay. So please note the questions down if you haven't, and try them. We will continue next time. Okay. Yeah. This week I'll try to make